Hi, my name is Matt Quijada, and today I will be giving you my speech on mechanical engineering. So my quote, scientific research is human endeavor. The choices of topics that we research are based on our biases, our beliefs, and what we bring, our cultures, and our families. The kinds of problems that people put their talents to solving depends on their values. By Dr. Clifton Poudry. And this quote is particularly important to just engineering and just STEM as an entire field, because especially for students like us going off to college, we kind of look into our major, and not many of us can deny that we do look at the starting salary of some of those. And so a lot of people look at those STEM salaries and they're like, wow, I can make $100,000 right out of college. And so I think it's important for people not to lose sight of the ultimate importance of what they're doing, which is kind of more the value of what they're doing, not the monetary value of what they're doing. Quick about me. I'm a senior here at Frisco High School. I'm in the drumline and jazz band, and I play in band. I'm heavily involved in music in and outside of school. I play in my church's youth band, and I will be going off to college majoring in mechanical engineering. I don't know specifically where I'm going yet, but I can tell you that I'm leaving Texas. So kind of my first semester was spent moving between different engineering disciplines. I wasn't sure exactly what I wanted to do. So the first thing I started researching was materials science and engineering. So I first learned about this when I attended a summer camp at the Missouri University of Science and Technology. And so actually those little spheres right there were kind of one of the things that got me interested in materials science. So basically what those are, they're tiny glass beads that are less than like a micrometer long. And basically what they do is they irradiate them, and they shoot them up into an area of the body. I think this one's most commonly used for liver cancer, and because of their size, they actually get stuck in the capillaries, which are this, I don't know too much about biology, but they're like the smallest whatever. And so basically because they get stuck, they can kind of treat that very specific area, which is kind of a cool innovation for cancer just treatment, because normally the problem is that you can't target one area, you kind of affect the body as a whole. But ultimately, when I started researching materials science, I found that the job opportunities were extremely limited. The job expansion was less than 1% in a year. So I kind of figured that was too narrow of a field to study for now. Maybe later on if I wanted to specialize, but I think I need to generalize a little bit. So from there, I moved on to chemical engineering, mostly because a lot of people who say if you're interested in material science, chemical engineering is kind of the broader major that includes that. And so I was doing a lot of research, and I kind of, going into ISM, I knew at the end of the year I wanted to create something very real. I can't really do research stuff, and so I kind of figured that if I wanted to create a viable product, it would be very difficult, and if I did create something, I would have to do toxicity testing and all this stuff to make sure that whatever I created didn't cause cancer in other people. That would be really stressful to deal with, and I don't think I could do that. And one of the kind of aha moments was that I realized I wanted to get into engineering because I liked physics and not really that I liked chemistry. And so just kind of thinking of that, I moved on to mechanical engineering. One of the other kind of catalysts that led to me switching to mechanical engineering was my visit to Bell Helicopter. And so I asked them kind of what their favorite part of mechanical engineering was, or I guess it was aeronautical engineering. And they said the design aspect is the most fun usually for them. And so I kind of thought about that some more, and I realized that was the aspect of engineering that interested me the most. So I figured I would look into mechanical engineering. Another reason is that mechanical engineering encompasses many other engineering disciplines. So I actually, and I'll talk about it in a second, but I interviewed a materials engineer. I found out that he actually has no materials background. He just has a mechanical engineering degree, but he still got the job. So my interviews. My first interview was with Randall O'Burl. He works at Raytheon. He's a mechanical engineer, but specifically he works with RF circuits, which is radio frequency. Just real quick, one of the problems that I had throughout my interviews is that I wasn't really sure what to ask specifically, just because I don't have an engineering degree. So I kind of asked them a lot of questions focused on the design and just the gritty work of mechanical engineering. But the problem was that many of these people were management people, so they didn't actually do a lot of the hands-on work. They were managing other engineers. Another person I interviewed was Sean Coffey. He works for a startup called MEMS, which their mother company is Honeywell. So they're not really a startup, but he was a chemical engineer. And he had a curious little bit of information. I was talking to him about colleges, and he told me to go to Texas Tech because private schools were just kind of a waste of money. Although I don't believe that entirely, it was kind of important to take into account thinking about kind of weighing the cost of a tuition versus what I really think I'm going to be getting out of it. Especially you hear stories of people going to private universities and graduating with degrees, and they still can't even find a job. So I still needed to consider that. Chris Wu and there were a couple other associate engineers that I met at Bell Helicopter. Like I mentioned earlier, they were kind of the ones that showed me what mechanical engineering was more about, and so that kind of got me interested in it. Dustin Miles was the materials engineer that I talked to, and he's the one that had a mechanical engineering degree, but he ended up working in materials just because he applied to the job. And then the last person was Mike Albrecht, and he's actually not an engineer by trade, but I'll explain why I kind of went with him as my mentor. He has a computer science degree from Notre Dame, and he works for AT&T. So Mike works at this branch of AT&T called the Foundry, and basically what AT&T wanted to do was they started these separate branches of AT&T that were able to simulate what a startup was doing. So Mike is an innovation coach, and so what they do is they bring in businesses that have an idea that they think can kind of change the industry. And so what Mike does is he works with this company for a 6 to 12 week period, and if their project is worth anything, then AT&T will kind of sponsor them and take on whatever technology they develop or intellectual property. And so that's kind of what they do. And so it's kind of ideal for an ISM student because for someone like Mike, he works on a very small time frame. And so given only a semester, it kind of just makes sense that I work with someone that's able to do that. And then another reason is that in the AT&T Foundry, they have several engineers with different backgrounds. So not only will I work with Mike, but through Mike, I can go upstairs and talk to a mechanical engineer or electrical engineer and kind of get their perspective on whatever I'm working on. So my original work. So common to engineering and really anything that people work in is that they have to identify a problem. I mentioned earlier that I was heavily involved in music, so it kind of made sense to me that the easiest thing for me to work on was a music-related problem. And I'll explain some of this some more, but one of the things that guitarists look for when they're playing is kind of a cool effect is being able to infinitely sustain a guitar note. And so I'll show you that's kind of what I did was I created a handheld device that was able to emulate the action of a bow. So finding the solution. I had already known about a process that could do something similar, but I didn't know there was a handheld device. Upon research, I found a product called the eBow, which basically does exactly what I did. But this was actually good because by taking a device and modeling it, I was able to only worry about the technical aspects of building something, which I can explain. So kind of how the eBow works. So first thing to understand about microphones and headphones is that they're the same thing. So if a headphone has a large enough coil, you can actually use it as a microphone. The same principle applies for, nice. The other way around, the only problem is that the coil, you can go. the coil on a microphone is usually too small to actually amplify a sound for you to be able to hear it. So the next thing to talk about is feedback. Has anyone ever been talking on a microphone and you get in that one spot where it like feeds back and there's all that loud noise? Yeah. So basically what that is, you can see this diagram over here. So the microphone is taking in an audio signal, which could be anything from like a breath of air to absolutely nothing. It just has to be something to trigger it. It takes that sound, it amplifies it, comes out with the speaker, and then it amplifies it some more. So basically what's going on is that you're creating an audio loop of the same frequency, and that's why it becomes so loud and it's one tone. It's kind of like if you've ever taken a document camera and you pointed it at its own screen, and then you kind of see that effect where it kind of multiplies what's going on the screen. It just looks weird, but it's in audio form. So that's gonna come in handy for sustaining one note on a string. The next thing to understand is how a pickup works, and I know that looks like a little physics 2 diagram, but like don't pay attention to anything. So basically the only thing to understand about a pickup is that it basically works in the same way as a microphone. And so if a microphone and a speaker work the same way, a pickup can work as a speaker. But specifically, the one thing that pickups do differently than microphones is that instead of taking the air vibration and turning it into electrical signal, they take the magnetic vibration of a string. And so just quickly explaining, when you move something magnetic through a coil of copper, it creates an electrical signal and then it sends it out. So that's basically how it works. So if you see over here, this is actually my first prototype. It's okay. If you want to pass that around so people can look at it. So basically, if you imagine this first pickup is kind of serving as a microphone, and this second pickup kind of serves as the speaker. And so basically, by using the feedback principle that I explained earlier, it's able to repeat one frequency and sustain a note. So before I go on, I just wanted to demonstrate. So just to compare, this is without sustaining the note. You can hear within seconds the note already dies. Yeah, so without even having to pluck the string, I was able to get the string going and basically keep it going for as long as I wanted to hold it there. Yeah. Oh, and this is basically, this is the schematic that I followed. The only thing you need to get out of this is that this is the input and this is the output, and all the fancy stuff is in here. So I kind of went through 3 different iterations of this product. The first was I used this thing called a breadboard, and actually I don't use it. I don't have it right now because my dad took it and he's using it for his own project, but it's actually right there. So basically what a breadboard allows you to do is you can put together a circuit without having to solder together the joints. So basically you can easily manipulate things without making anything permanent. And that soldering, for anyone that hasn't done work with circuits, it's basically when you want to join together 2 ends of a wire, you kind of twist them together, or you just put them together, and you superheat a conductive metal onto it. And so the metal is in liquid form, and then it forms around the joint, and then it solidifies, and then now you have a solid joint. It's kind of like working with a glue gun, except like 3 times hotter. So it gets around 600 to 700 degrees. So if you burn yourself, it really hurts, which I got to learn about, which is fun. The third kind of material that I used was balsa wood, and if you pass it around, you can kind of see that's. Did everyone see it? I just kind of needed to create an enclosure because ultimately I had these 2 coils that were kind of moving around freely, and if I wasn't holding them in place, the device wouldn't work. So the second prototype, instead of a breadboard, I now use something called protoboard, and this uses soldering, so it's much more permanent. So basically, I took the circuit that I put together in the breadboard and I condensed it down. You can see it over here. And actually, here, if you want to pass it around real quick. You can see on the bottom of that I have all the soldering joints. And so that's kind of, it was a more permanent process. And also in this second prototype, I was able to condense the device. If you look earlier, it's kind of here and then it's here. And if you see me using it, I'm holding it, but then the entire circuit's over here. So it kind of wasn't ideal to use. Now that it's handheld, I'm getting more towards the target of the problem I wanted to solve. So the final version, which actually I wasn't able to complete yet because the main thing I'm waiting on is 3D printing. So I actually learned how to use a computer-assisted design software to design the 3D enclosure for the product. And basically, once that's finished, I'll be able to print that and then put the circuit into it, and I'll have the final device. If you can see right here, this is all the coding language. So normally in a CAD software, it's actually very easy and user-friendly. You just kind of manipulate the shapes. But my mentor, being a computer science guy, wanted me to learn how to write the code for every shape and learn how to do that, which is actually a lot more painstaking than just moving a square around. Over here, I'm doing frequency testing. So that's that little oscilloscope. And actually, there's a camera behind me because that day AT&T brought in a media team and they saw me working on it. They're like, "Oh, that looks cool. Can we talk to you about that?" I was like, "Okay." So I basically, wherever, I don't know where that's going to be, if it's going to be on like some commercial somewhere, but I got some experience with that, which is cool. But so the frequency testing, I just wanted to make sure that the circuit was working effectively because there are a lot of people know about frequencies that are inaudible, kind of like what dogs can hear but what humans can't hear. So basically, if the circuit is wasting energy on amplifying those frequencies, it's wasting energy because you can't even hear that frequency, and so it wouldn't be working. Can I get that back? Ugh. Ugh. Thank you. Just a fun little before I finish. So kind of the advantage is now, even though I don't have a hand to pluck, I only need to use one hand to move around and play the notes. Yay! I just wanted to show you that so you could see the fun aspect of what I was doing. So the significance of my original work. So I mentioned earlier that by modeling a device that already existed, I didn't have to worry about the creative aspects. So I was able to learn the technical aspects of putting together a circuit, designing an enclosure, and then learning the 3D CAD coding for creating the enclosure without having to worry about what problem or how I'm going to solve the problem. And then over here, I just kind of listed the different, going back to how mechanical is kind of an overarching degree. I kind of learned about electrical engineering, mechanical engineering, and computer science, which is often considered a branch of engineering. Just showing how mechanical engineering is kind of broad and you can do a lot of things within that field. So moving on to my final product, basically I'm going to take the application of the skills that I learned making my original work, and then I'll be able to apply that to now solving my own problem with my own new solution. And that word "new" is key because, as you can see in my original work, I kind of copied a solution, but in my final product I will now be identifying a problem, finding my own solution, and then now implementing that solution. And then just real quick, music or physical therapy. I kind of have two paths to go down for my final product. One would be the music-related one, which would be creating some kind of music production equipment that would make things easier, or physical therapy, which I would be partnering with someone who's studying physical therapy and working with them to make a certain process easier for recovery in physical therapy. That is my speech for mechanical engineering, and thank you for listening to me.